We're going to look in this section at differentiating y equals sin x from first principles. The method is exactly the same as differentiating x squared from first principles, which is in another differentiation chapter. You could review that if you don't understand this video. Let's look at the sin x curve. We need a section of curve, so we're going to draw some axes and look at a section of the sin x curve. Let's take a point on the curve, and we want the gradient of the curve at this point. We know that that means the gradient of the tangent to the curve at this point. Let's call this point xy. To approximate the gradient of this tangent, we take a chord, so we need a second point a little bit away from x at x plus delta x, and the y-coordinate is y plus delta y. So the gradient of the chord here is used to approximate the gradient of the tangent. So we want the gradient of the chord. The difference in the y-coordinates is delta y, and the difference in the x-coordinates is delta x. The gradient of this chord is delta y divided by delta x. The curve is y equals sin x. So another way of looking at this point is that its coordinates are x and sin x, since y is the sine of the x-coordinate. At this point then, the coordinates are x plus delta x, and the y-coordinate is the sine of x plus delta x. It follows that the gradient of the chord is delta y over delta x, which is the sine of x plus delta x, take away the sine of x, divided by the difference in the x-coordinates, which is delta x. So all we've done so far is say that the gradient of this chord is the difference in its y-coordinates divided by the difference in its x-coordinates. And this is something we should know. To deal with this, we need to use a trigonometric identity. The sine of a plus b, we know, is the sine of a times the cosine of b plus the cosine of a times the sine of b. Therefore, the sine of x plus delta x can be expanded, giving us the sine of x times the cosine of delta x plus the cosine of x times the sine of delta x. Take away the sine x, all divided by delta x. The definition of dy dx is that it is the limit as delta x tends to 0 of delta y over delta x. Geometrically, delta x tends to 0 means the distance between the 2 points that we used on the curve shrinks. As the 2 points get closer together, the gradient of the chord becomes a better approximation to the gradient of the tangent. Delta x tends to 0 means that we shrink the 2 points until they are virtually the same point. We're interested in what happens as delta x tends to 0. If we consider the cosine of delta x, then if the calculator is in radian mode, as delta x tends to 0, the cosine of delta x tends to 1. Try it on your calculator. Put the calculator into radian mode and start typing in very small values of delta x. Take their cosine. You'll see the cosine of 0.0001, for example, is very close to 1. So in the limit as delta x tends to 0, the cosine of delta x tends to 1. This result for the cosine of delta x works whether or not the calculator is in radian mode. However, if we look at the sine of delta x, we must be in radian mode for this result to work. We can see that the sine of delta x tends to delta x as delta x tends to 0. Just try some very small values of delta x. Do the sine of 0.1, the sine of 0.01, the sine of 0.001, and so on, and you'll soon see that this is true. As delta x gets very small, the sine of delta x gets very close to the value delta x. Given these results, we can simplify our expression. dy dx, remember, is the limit as delta x tends to 0, so we know the cosine of delta x has become 1, and so the first term is just sine x. The sine of delta x has tended to delta x, so the second term becomes cos x delta x, and we have the minus sine x, all divided by delta x. The sine x's cancel, giving us cos x times delta x divided by delta x, and the delta x's cancel, giving us just cos x. So if we differentiate y equals sine x, we get dy dx is cos x. By a similar method, we can show that the differential of cos x is minus sine x.